Good morning, everyone, and welcome. I'm delighted to have you here today. We will be discussing the validation of moist heat sterilization, a crucial process in ensuring safety and efficacy. The presentation is titled Validation of Moist Heat Sterilization, and it is presented by Dr. S.K. Singh, PhD. I'll be guiding you through the key concepts, methods, and standards involved in this important area. Over the next few slides, we'll cover the principles, procedures, and best practices to ensure effective sterilization. Let's get started. Let's start by looking at sterilization. Sterilization is essentially the process, whether physical or chemical, that eliminates all viable microbes. This includes even the most resistant bacterial spores, which are often the toughest to destroy. The goal is to ensure that no living microbes remain on a fluid or solid. There are several methods we use for sterilization. For example, steam treatment at 121 degrees Celsius is quite common, especially in medical settings. Dry heat at 230 degrees Celsius is another option, often used for instruments that can't be exposed to moisture. We also have chemical methods, like flushing with sterilizing solutions such as hydrogen peroxide or ozone, which are effective for delicate equipment. Additionally, irradiation and filtration are used, particularly for heat-sensitive materials. Moving on to sterility, this concept is about reducing contamination levels to a very low probability, specifically less than 1 in a million, or 10 to the minus 6. This means that the chance of any surviving microbes is extremely small, ensuring safety and purity. Finally, let's talk about D-value. This is a critical term. It refers to the time in minutes required to achieve a 90% reduction, or a 1 log reduction, in a specific microbial population under defined lethal conditions. For steam sterilization, this D-value is determined at a consistent temperature, which helps us standardize and predict sterilization effectiveness. Understanding these concepts helps us ensure that our sterilization processes are both effective and reliable, which is essential in maintaining safety and quality in any setting. Let's start by talking about the F value, which is also known as the lethal rate or the instantaneous foe. The F value is a key measurement of how effective a sterilization process is. It essentially tells us the equivalent amount of time at a specific temperature that's needed to achieve sterilization. When we refer to F, T, Z, we're talking about the equivalent time at a temperature T, and it's calculated using a particular Z value. This helps us compare sterilization effectiveness across different conditions. Next, we have the foe value, which stands for the accumulated foe. This is defined as the total number of equivalent minutes of steam sterilization at a standard temperature of 121.1 degrees Celsius. The calculation uses a Z value of 10 degrees C, which helps standardize the process. This way, we can quantify the sterilization process over time, ensuring consistency and safety. Finally, let's look at the Z value itself. The Z value indicates how much we need to change the temperature to alter the D value by a factor of 10. In other words, it measures the temperature sensitivity of the microorganism or process. Understanding the Z value allows us to fine-tune sterilization conditions efficiently, ensuring we achieve the desired level of microbial kill without overexposing the product. Together, these concepts, F value, foe, and Z value, are fundamental for designing and validating effective sterilization processes, which is crucial for maintaining safety and quality in our operations. When we talk about bioburden sterilization, the goal is to achieve a probability of survival of less than 1 in a million, or 10 to the power of minus 6, for the most resistant bioburden we expect in our load. This means our sterilization process must be robust enough to handle even the toughest microorganisms. To do this effectively, we need detailed information on the numbers of bioburden present and their heat resistance characteristics. Additionally, ongoing monitoring or control is essential to ensure these conditions are maintained consistently over time. Now, moving on to overkill sterilization, this approach ensures a minimum 12 log reduction of a resistant biological indicator, or BI, which has a known D value of at least 1 minute. In simpler terms, we're aiming to reduce the bioburden by a factor of 1 trillion, which is quite a stringent requirement. Interestingly, this method requires less detailed information about the bioburden itself, focusing mainly on the process's ability to achieve that significant reduction. Finally, when we consider bioburden or bioindicator sterilization, we're aiming for a probability of survival of less than 1 in a million, just like with bioburden sterilization. But here, we're demonstrating this reduction using a resistant bi with a known d-value. It's important to note that the bi may not always be fully inactivated, but the process should reliably show that the bioburden is being reduced effectively. This method also requires us to have information about the numbers and heat resistance of the bi, along with ongoing monitoring to ensure consistent control over bioburden levels. Overall, these methods highlight different strategies to ensure our sterilization processes are both effective and reliable, each with its specific requirements and focus areas. Let's talk about gravity displacement. Essentially, this process relies on the difference in density between air and steam. For example, at 20 degrees Celsius, the density of air is about 1.2 grams per liter, while at 100 degrees Celsius, the density of steam drops to around 0.6 grams per liter. This difference in density is what allows the steam to displace the air in the sterilizer. Now, the effectiveness of removing air depends quite a bit on how quickly we supply the steam. If we supply steam too rapidly, we might create air pockets that get trapped, making it harder to remove all the air efficiently. Conversely, if the diffusion of steam into the space is too slow, it becomes more difficult to push out that residual air altogether. To address this, we use specially designed steam traps. These traps are capable of allowing large volumes of air to pass through without getting stuck, ensuring that the sterilizer is properly vented. This is critical during the sterilizer cycle because thorough air removal ensures that the sterilization process is effective and uniform throughout. Now, let's take a closer look at the pre-vacuum cycle. This is considered a more effective sterilization method because it uses either a mechanical vacuum pump or a steam ejector to remove air from the chamber. By achieving a vacuum as low as 15 to 20 millimeters of mercury and maintaining it for about 8 to 10 minutes, we ensure that all air is thoroughly evacuated, which is essential for proper steam penetration and sterilization. Moving on to the pulsing cycle, this involves a series of alternating steam pulses and vacuum excursions. This cycle is particularly useful when sterilizing large volume parenterals, as it helps to remove residual air and improve the effectiveness of the sterilization process. During this cycle, an air-steam mixture is introduced, which helps displace trapped air more efficiently. Additionally, because of the significant expansion of air or nitrogen in the headspace above the liquid, an air injection is often necessary. To manage this, we use a well-mixed chamber equipped with a fan or a rain effect created by an external pump with cooling. This setup ensures that the chamber contents are evenly mixed, preventing localized hot spots and ensuring uniform sterilization throughout. Overall, these cycles are crucial components of sterilizer operation, ensuring we effectively eliminate microorganisms while maintaining the integrity of the products. When we're considering factors into account for sterilization, the first thing to look at is the nature of the load. This includes whether we're working with porous materials or heat-sensitive products. For example, delicate biologicals or pharmaceuticals that can't withstand high temperatures require a different approach compared to more heat-stable items. Next, we need to think about the type of sterilizer we're using. Different sterilizers have different capabilities and limitations, so selecting the right one is crucial. Additionally, the employed containers and closures play a significant role because they can influence heat distribution and penetration. Now, for heat-stable products, we often use an overkill approach, meaning we apply a sterilization cycle that exceeds the minimum requirements to ensure safety. Conversely, for heat-liable products, we rely on a bioburden approach, which focuses on reducing the microbial load to acceptable levels without risking damage to the product. Let's talk about bioburden studies. These involve measuring the number of microorganisms present initially, giving us a baseline to work from. D-value studies are also important. They tell us how resistant certain microorganisms, especially highly resistant spore formers, are to the sterilization process. We often use a biological indicator evaluator resistometer, or BIR, to assess this resistance. When conducting studies, we inoculate spores into the actual solutions, or, in the case of solid materials, use pre-cut strips. This helps us simulate real-world conditions as accurately as possible. Finally, cycle development is a critical phase. It involves fine-tuning the sterilization process based on these studies and factors, ensuring that the cycle is both effective and efficient for the specific load we're sterilizing. Now, let's look at the setup for autoclave validation. First, we have the validation nozzle and adapter, which are essential for ensuring that the sterilization process is evenly distributed and effective. Next, we use a data logger, which is a multi-channel device capable of digital output to monitor and record temperature data in real time. This helps us gather precise data during validation. We also incorporate biological indicators, or BIs, along with biological challenges, to verify that the sterilization process effectively kills all microbial life. The loads we sterilize are carefully prepared and monitored to ensure consistency. For temperature sensing, we rely on T-type thermocouples, which are copper constantin and encased in flexible sheaths for durability and accuracy. We also use premium-grade wires that provide an accuracy of 0.1 degrees C, crucial for precise monitoring. Regarding temperature standards, our sensors are traceable to recognized standards like the National Bureau of Standards, IPR, and HTR, ensuring the reliability of our measurements. When calibrating thermocouples, we do so at two key temperatures, 0 degrees C and 130 degrees C. We apply correction factors to account for any deviations, and we ensure the stability of the sensors within 0.03 degrees C with an overall accuracy of 0.5 degrees C. Finally, preparing for validation involves meticulous calibration and setup to ensure all components work harmoniously. This thorough preparation helps us maintain high standards and confidence in our sterilization process. Now, let's take a closer look at the types of studies involved in validation. First, we have bioburden determination studies, which are essential if applicable, to understand the microbial load on products before sterilization. Then, there are empty chamber heat distribution studies, helping us verify that heat is evenly distributed throughout the sterilizer chamber, ensuring effective sterilization. Next, we consider container mapping studies, again if applicable, to assess how sterilization parameters perform with specific container types. Loaded chamber heat penetration studies are also crucial because they demonstrate that the sterilant reaches all parts of the load effectively. Microbiological challenge studies are designed to evaluate the sterilizer's ability to inactivate resistant microorganisms, confirming the sterilization process's efficacy. We also need to evaluate the cooling water used for the drug product, if applicable, to prevent contamination or process interference. Additionally, integrity testing of vent filters is performed to ensure they maintain their integrity throughout the process, preventing microbial ingress. Of course, all these studies must meet specific acceptance criteria, which serve as benchmarks to confirm the process is consistent and reliable. And when documenting all this, references to standards and previous validations are important, along with the review and approval process to ensure compliance. Moving on to the protocol itself, it must clearly outline the objectives of the validation, defining what we aim to achieve. Responsibilities of validation personnel and operating department personnel should be clearly assigned, ensuring everyone understands their roles. The protocol should also identify and describe the sterilizer and its process control system, including relevant SOPs. Calibration of instruments is critical, so SOPs and descriptions for equipment calibration should be included, along with identification and calibration procedures for temperature monitoring devices. The validation protocol must also be comprehensive, covering all aspects needed to demonstrate the process's robustness. In summary, a well-prepared validation protocol is the backbone of a successful validation, ensuring clarity, accountability, and compliance throughout the process. Let's look at how we demonstrate the temperature uniformity and stability of the sterilizing medium throughout the sterilizer. We conduct tests on both the empty chamber and the loaded chamber, using both the maximum and minimum load configurations to ensure consistency across different conditions. The key acceptance criterion here is that the temperature variation should be within plus or minus 1 degree Celsius of the mean temperature. To ensure reliability, we perform 3 separate runs to gather consistent results. When placing the thermocouples, we aim for a representative distribution, covering geometrical points, the exhaust drain, and areas adjacent to the control sensor. Typically, we use at least 10 probes, but often we have between 15 to 20 probes to get a comprehensive picture. This process, known as heat distribution studies, is critical because it helps us verify that the sterilizing medium is evenly distributed and stable throughout the chamber. This way, we can be confident that our sterilization process is effective and uniform, which ties directly into the overall quality and safety standards we strive to meet. When conducting the loaded chamber heat distribution test, it's important to position the thermocouples in the same locations we used for the empty chamber test. This consistency helps us accurately compare how heat distributes under different conditions. Remember, avoid contacting any solid surfaces with the thermocouples, as that can affect the readings. Also, do not place them inside any containers, since that could alter the heat flow and skew our data. It's crucial to obtain data at regular intervals throughout the test. Consistent timing ensures we capture the heat distribution pattern accurately over time. By following these guidelines, we can ensure our measurements are reliable and comparable, which ultimately helps us understand how heat behaves in loaded chambers. This step is vital for validating our thermal models and improving the overall design of our system. To determine the coolest point within the liquid-filled container, I recommend conducting temperature mapping across all the different container types, sizes, and fill volumes that need validation. This ensures we understand how temperature varies throughout the entire system. The number of thermocouples we use will depend on the container volume. Larger containers generally require more measurement points to accurately capture the temperature distribution. Sometimes, it's possible to use a single thermocouple at different positions if we're working with a smaller autoclave or retort, which can save time and resources. Additionally, penetration thermocouples should be strategically positioned at the cold spot, which is the point with the lowest temperature, often referred to as FO. Pinpointing this area is crucial because it's typically the last spot to reach the desired sterilization temperature, ensuring the entire container is properly sterilized. Overall, container mapping is a vital step in validating our process, helping us identify any cold spots and confirm uniform heat distribution. This way, we can ensure product safety and process consistency across different container configurations. When we talk about regard to product stability, we're essentially looking at the cumulative effect of heat over time, specifically through what we call the lethal rate. This is a way to quantify how effectively heat kills microbes during processing. The idea is to sum up the lethal rate over the entire process duration, based on the temperature at each point in time. The lethal rate itself can be calculated from temperature data using a specific formula. It involves the temperature at the process time, 2, the temperature of the coldest point, TB, and a parameter called Z, which reflects the temperature change needed to change the microbial death rate by a 10-fold factor. The formula looks like this. L equals log base 10 of to minus TB divided by Z, or alternatively, 10 to the power of that same ratio. This gives us a clear, quantitative way to assess how lethal the heat treatment is at any point. Now, to ensure the process is effective, we need to identify the coolest spots within our load and configuration. These are the critical points, because if they reach the necessary lethality, the entire load is properly sterilized. Our goal is to make sure these points are consistently exposed to enough heat to achieve the desired microbial kill. Before we start any heat penetration studies, it's important to determine both the maximum and minimum load configurations. This helps us understand the range of conditions the product might experience, ensuring our process is robust enough across different load scenarios. When placing probes, especially for temperature measurements, we need to be strategic. The container at the cold spot should be uniformly distributed throughout the load. This ensures we get an accurate picture of temperature variations across the entire load. Finally, we position penetration thermocouples at points within the equipment that are suspected to be the most challenging for steam heat to penetrate. These are typically areas where heat might lag or where temperature might be lower, so monitoring these spots helps us verify that heat penetrates effectively and uniformly. Overall, these steps are essential in heat penetration studies to validate that our sterilization process is both effective and consistent, safeguarding product quality and safety. Biological challenges are an essential part of heat penetration studies because they help us demonstrate the actual effectiveness of the sterilization process. Essentially, we want to see how well the cycle kills microorganisms, and that's where these challenges come into play. Typically, we use certain microorganisms that are known for their resistance. For overkill methods, Bacillus stereothermophilus and Clostridium sporogenes are common choices because they are highly resistant spores, making them reliable indicators of sterilization success. In terms of bioburden, we often use calibrated biological indicators, or BIs, which are derived from environmental and process isolates, like E. coli. These BIs help us simulate real-world contamination levels and ensure the process is robust enough to handle typical microbial loads. The type of BIs we use can be spore strips or spore suspensions, which are introduced into the suspending medium. This allows us to accurately assess whether the sterilization cycle can effectively inactivate these microorganisms under actual processing conditions. It's important to remember that microbial challenge studies are conducted simultaneously with heat penetration studies. This concurrent testing ensures that as we verify the temperature reaches the necessary levels, we also confirm the microorganisms are being effectively killed. Overall, these microbial challenge studies are a critical component in validating sterilization cycles, giving us confidence that the process is both effective and reliable in ensuring safety. Let's take a closer look at the common elements found in all reports. First, each report should clearly identify the task by its number. This helps us keep track of each specific project or experiment. Next, there's a reference to the protocol used, ensuring that everyone understands the procedures followed. Then, a brief summary of the operational conditions experienced is provided, along with how those conditions were controlled throughout the process. This part is crucial because it shows how we managed the environment to stay within acceptable ranges. Following that, there's a procedure outlined for maintaining control within those approved operational limits, which helps ensure consistency and reliability. We also include a summary and analysis of the experimental results, highlighting the key findings and insights. If there were any deviations from the planned procedures, these are briefly described, so we understand any anomalies or unexpected events. The report then culminates in a conclusion that synthesizes the findings, and a review and approval section to verify that everything has been properly vetted. It's important to note that cycle development reports are generally not part of the validation report, as they serve a different purpose. Altogether, these elements form a comprehensive and structured way to present validation data, ensuring clarity, traceability, and confidence in the results. This consistency across reports supports the overall integrity of our validation process. Let's take a closer look at some of the key components involved in maintaining the effectiveness and reliability of sterilizer operations. First, we have a routine calibration program for all instruments that are critical to the sterilizer and its support system. This is essential because accurate measurements ensure that sterilization processes meet the required standards consistently. Next, there's a preventative maintenance program, which includes periodic operational rechecks and comparisons to the original qualification records. This proactive approach helps us catch potential issues early before they impact sterilization effectiveness. We also emphasize routine monitoring of bioburden, which is the microbial load on items before sterilization. Additionally, optional periodic biological indicator, or BI, challenges can be performed to verify that sterilization is achieving the desired microbial kill. Keeping detailed operating records and equipment logs is another vital aspect. These records provide a traceable history of operations and maintenance, which supports accountability and troubleshooting. When it comes to process and equipment changes, we have change control procedures in place. These procedures include reviews to determine if additional validations are necessary, ensuring that any modifications do not compromise sterilization efficacy. Finally, ongoing validation, maintenance of validation records, and continuous monitoring are integral parts of a robust sterilizer management system. Together, these measures help ensure that sterilization remains effective, compliant, and reliable over time, reinforcing the overall safety and quality of our processes. Let's talk about the incubation period for the sterility test, specifically comparing 7 days versus 14 days. The longer period, of course, provides a higher assurance of detecting any contaminants, but it also extends the testing timeline. Balancing the incubation duration is crucial for efficiency without compromising safety. Next, I want to highlight what the USB offers in terms of guidance. They provide detailed information on the critical parameters required for parametric release, which is a method that can sometimes help streamline the process by relying on validated in-process controls instead of full sterility testing. We also need to consider how often and to what extent revalidation is necessary. This is important because changes in manufacturing processes or testing methods may require us to revalidate our sterilization procedures to ensure ongoing compliance and effectiveness. Another key point is the verification of the D-value of biological indicators, or BIs. The D-value tells us how resistant a microorganism is to sterilization conditions, so verifying this ensures that our indicators are reliable and that our sterilization process is effective. Speaking of BIs, there's ongoing discussion about using alternatives to B. stereothermophilus. Exploring other organisms can sometimes offer advantages, but it also raises questions about comparability and validation, making it a somewhat controversial issue in the field. All of these points tie back to our overall goal, ensuring sterilization processes are robust, validated, and compliant. Staying informed about these nuances helps us make better decisions and maintain high standards in our sterilization practices. For further support, please contact us. We're here to help you with any questions or additional information you might need. Don't hesitate to reach out. We want to ensure you feel confident moving forward. Thank you so much for your time and attention today. We appreciate your commitment to this project and look forward to working with you.